Welcome back, everybody. In this section, we're going to be taking a look at our next Layer 2 topic inside of the Enterprise set of videos for Layer 2, which is going to be spanning tree protocol. Now, if you've been dealing with spanning tree protocol before, great. You know how much it can be a pain in your butt. If you've never dealt with spanning tree protocol before, it's okay. I'm going to give you guys a high-level overview as to what spanning tree protocol is and some of the topics that go along with that. So, I'm going to spend a little bit of time going through some of the understandings that you need to have in order to get just a general understanding of what spanning tree protocol is all about and things like that, because, I mean, you definitely need to understand some of the basics to it. So, spanning tree protocol and its core functionality is to prevent layer 2 loops. So, in other words, you don't want to have traffic going from switch 30 to 29 to 31 to back to 30. That's just a bad thing. So, in order to fix that, what you're going to end up having is scenarios where switch 30 is going to send traffic to 29, 29 is going to send it to 30, but 31 will not be able to send it back to 30. So based off of a two-part setup, one is going to be a priority, and the other one is going to be a MAC address. This is going to make up what they call the bridge ID. Basically the switch identification. That's all it basically is. Somebody asks you for your license and registration. Are you Joe Blow that should own car Chevy Malibu? Basically is what it's saying. And what's going to end up happening is, based off of that information, you should have a situation where whichever side is the lower of the two. So by default, all the priorities on all the switches are set to the same, 32768. The MAC addresses will be different on a per switch basis. And what that's going to do is the lowest MAC address from a left to right perspective, whichever switch has the lowest MAC address, by default will become what they refer to as the root bridge. The root bridge, think of like that as the center of the universe for a VLAN information setup, where you basically have, let's pick on switch 30 for the moment because it's the top right. If switch 30 is our root bridge, in a normal implementation, he's going to be the guy that sends out all of the information that everybody else needs to know about. They call this a topology change notification Bpdu, or a TCN. So what's a Bpdu? Well, a Bpdu basically is a way for one switch to tell another switch, hey, here I am, and here's my bridge ID information. Here's the port ID information that I'm connecting to you with. So in other words, switch 30 would send information to switch 29 saying, hey, I'm switch 30. And I'm connected to you via gig 02 and gig 03 on my side, and that's the information you need to know about. My priority is this, my base MAC address is this, and I have this many VLANs. And this is going to be done per VLAN. So it's why they refer to spanning tree as per VLAN spanning tree, because it sends out all this information per spanning tree, per VLAN on every trunk link that's configured on the switch. Now, the drawback to that is for every VLAN you send, every VLAN that's created, you have to send a Bpdu per VLAN. So if you only have a few VLANs, not that big of a deal. But if you have multiple VLANs, that could suck. So that's why it can be a bad day if you're not sure really how to handle something or how to go about doing it. So in terms of how the spanning tree implementation comes into play, everybody's going to have information about what's going on. That information is going to be the bridge ID. The idea is if switch 30 sends information to 29, 29 takes that information and propagates it to 31. 31 gets it, then 31 can send it to 30. Well, when 30 receives it, every Bpdu and all the information that's included inside of that, 30 is going to receive it and go, okay, well, the originator of that was myself. So if I see my own information coming back in, I'm going to know that that's potentially a loop, and I'm going to block that port. So it could block gig 00 and gig 01, depending on the mode on a per VLAN basis of what that particular switch is trying to do. If the switch is a root bridge for that particular VLAN, then all of these ports are going to be referred to as designated ports. What's a designated port? A designated port is simply a port that forwards traffic. none of the ports are in blocking. They're all pushing data out on a pretty regular basis. As a matter of fact, they are all sent on every port, on every switch that's connected to the root bridge is going to be sending out a Bpdu every 2 seconds per VLAN. So if you only have a couple of VLANs, not that big of a deal. But if you have multiple VLANs, let's say 50 or more, then every 2 seconds you're going to be sending 50 Bpdus out every trunk length you have configured. And that happens on all 3 switches. It's can be configured to be a lot of overhead if you have a larger environment. Now, the port state and the device role are sometimes mutually exclusive or mutually destructive, depending on how you want to look at it. In other words, at switch 30 is going to be the root bridge. All of it's for every VLAN. Then every port on switch 30 is going to be in designated forwarding. That means that switch 29 and switch 31 are going to have other ports that are configured or set up based off spanning tree to be either forwarding or blocking. Now, what's a forwarding port? A forwarding port is always facing away from the root bridge. So it's always facing downstream. It's designated forwarding. And think of that as a downhill or it's a southbound facing port. Any ports that point towards the root bridge, also referred to as the root port, those are always going to be forwarding as well. And that's going to be one of the key aspects of this that you really need to understand is designated ports face away from the root bridge, root ports face towards the root bridge, and the alternative to all of that is going to be the alternate port, which is going to be in blocking mode. It's another way of getting to the same destination but with a higher cost. And that's how spanning tree figures out how everything is working in the network, what the port cost is. Now, every one of our switches has 2 connections to every other switch. So 30 connects twice to 31 and connects twice to 29. In other words, one of these ports, one of these switches is going to be blocked. And the reason that happens is to prevent the unnecessary flooding of information throughout the layer 2 environment. And in situations like that, that can be a bad thing. So you don't want to have 30 send traffic out 2 and 3 towards 29, 29 receive it and send it out 3 and 2 on its ports towards 31, and then 31 sends gig 00 and gig 01 information out those ports to switch 30. Switch 30 receives that information, and now we have a loop. That's the ultimate thing that we were trying to avoid. How do we avoid that? Well, depending on how things are working, 31 could be blocking gig 00 and gig 01. Or 30 could be blocking gig 00 or whatever the case might be. It might be multiple scenarios that could be coming into play depending on how everything is set up. The reason why I fall back to that is because things could be set up per VLAN basis, and we definitely we won't always know until we start looking at the implementation. So, with that being said, I'm going to create a couple of additional VLANs. I'm going to create, I'll just throw some numbers out there, and we'll create a couple of additional VLANs, and then we will go through and set up the spanning tree, and then we'll take a look at exactly how it all falls in together. I don't want to spend a ton more time on spanning tree protocol because I honestly hate talking about spanning tree, because in most of the environments that I'm seeing nowadays, most folks are moving away from it, especially in the data center. I'm seeing a lot more routing down to the access layer and trying to make the layer 2 environment as small as possible, make it only as big as you need it to be in order to get the job done, and bring your default gateways down as far south to distribution or the access layer as you can. As a matter of fact, a lot of organizations that I've worked with in the past have actually moved layer 3 down to the access layer, where there is no spanning tree protocol at all, or you're relying on routing protocol convergence, not spanning tree protocol convergence. Each one has its own pros and cons. I'm not going to really get into that too much right now, but that's basically how that would come into play. So with that being said, let's go ahead and pull up packet or secure CRT. And what I'm going to go ahead and do is I'm going to do a quick look at the show spanning tree here real quick. And we can see that we have a couple of different VLANs. We have VLAN 12, VLAN 11, VLAN 1. And right now we are the root for VLAN 1, VLAN 11, and VLAN 12. That's cool. And that makes sense because we are the lowest numerical switch, which might give, so we are 01D. Let's take a look at this guy and do a show spanning tree. We are 01D as well. Or sorry, we're 01E. And I bet you 31 is going to be 01F. And I was right. So 29 is going to be our root bridge. That's okay. That works out quite well. I'm going to go on to switch 29. And I'm going to create a couple more VLANs. I'm going to create VLAN 21, 22, 23, 24, 25, 26, 27, 28. So now I created a bunch of additional VLANs, and if I show history, let's go ahead and just create these VLANs on 30 as well. The reason why I want to do this is because I want to have these VLANs created so that when 31 gets them and show VLAN brief, we'll be able to go through and play around with the different spanning tree instances. So we'll be able to do root bridge here, root bridge there, secondary here, all that good stuff. So right now, if we were to do a show spanning tree, some of the stuff is going to be in forwarding mode, and most of it's already been figured out because we're in rapid spanning tree protocol, which is what we want to be in. We don't want to be in what they call PVST or IEEE spanning tree protocol, because then we're waiting a lot longer, 30 to 50 seconds depending on the scenario, closer to 30 more often than not than 50. But the idea is we have a scenario where 29, I bet you any money, is going to be show spanning tree. We're going to look at the root. This guy's the root for everything. That's okay though. Now, 29 is technically acting as an access layer switch in this design, so we want to modify this config a little bit. And the reason why we want to modify it is because we want 30 to be the root bridge for all the even VLANs and 31 to be the root bridge for all the odd VLANs. And then we can load balance that and say, you know what? In the event that 31 dies, we want 30 to be able to take over as a secondary root bridge for all the odd VLANs. And in the event that switch 30 dies, we want switch 31 to take over as a secondary root bridge for all the even VLANs. And I'll show you how to configure those. So this means that when we look at this output right here, we have, this is the root bridge information, and this is the current bridge that you're on information. So here we have the priority is 32793, which is 32768 plus the VLAN ID. So you take 68 and 25, you get 93. Now, the priority does not change. The priority increments as the VLAN numbers do. So as you continually add VLANs, whatever VLAN number you get, you add that to 32768. Voila, you have your VLAN, you have your priority. The MAC address never changes. It's always the same. So in order to influence how spanning tree protocol is going to determine which switch is doing what, in other words, who's the root bridge, who's not the root bridge, is by modifying the priority. So what I'm going to do is I'm going to come back over here to 30. I'm going to type in here spanning tree, and then for the particular VLAN, I can type VLAN and then the name. Let's say, for instance, I start off with 12. And I want to say we have a couple of different things. We can modify with the timers. I'm not going to mess with that because I can't stand dealing with timers, because unless there's a routing protocol that I can do some adjustments to, I don't mess with them. As long as you know what timers are doing what and how to adjust them, you're in good shape. The priority is going to be a numerical value in increments of 4096. So if you want to modify something, you would have to know the increment you want to drop it down to. I personally like using the root command, and it gives you a primary, secondary type of a scenario where you can say, you know what, I want switch 30 to be the primary root bridge for VLAN 12. So I just type in primary, and guess what? I can just hit the enter key and be good to go. Now the diameter means how many bridges between two nodes. What that means is if I have PC1 and PC2, how many switches can sit in between PC1 and PC2? If you want to have 2, the most you can have is 7. Spanning tree can calculate a loop-free path for dually connected or redundant connected switches. So switches connected in serial, or one after the other, each with 2 connections in between each one, up to 7 switches from start to finish. That's what that means. So I can create whatever I want. I'm not going to do that. I'm going to do that. Now by typing do show spanning tree, we're going to look at, we are not the root bridge for for VLAN 1 or for 11, but we are the root bridge for VLAN 12. See how that's how I modified that by bringing this into play here, 24588. That's our new root bridge, and that because he's got a lower priority value, he becomes the root. And the same thing with 31. I can come up here and I can type in spanning tree VLAN 11 root primary. If I go over to switch 30, let's look at do show spanning tree. I look at this guy here, 001F. If I look over at 30 here and I hit the up arrow, and I look at 11, I have the root is 001F. So that means it took advantage of it and went the direction it needed to. Now what happens if I want to be on 31 and I want to be the secondary for VLAN 12? So I can type in spanning tree VLAN 12 root, and I could say secondary. Now it doesn't actually show up in the config as an output as a show spanning tree, but if I do show run and give that a second to pull up, where this will pull up here is in global config, where here I'm saying for switch 31 I want to be the primary root bridge for VLAN 11. I want to use this particular priority value. For VLAN 12 I want to be the secondary root bridge using this priority value right here. The root primary, the root secondary commands are literally just a macro. It's a global configuration command that says, you know what, it's easy to type this command in, voila, there you go. Instead of you having to remember a priority value or anything like that. Now some people like to use 0 and 4096. That's okay. It has the exact same effect. Because all you're doing with the priority command of, the root primary is you're deducting 2 4096 increments, or 8192 from 32768, or whatever the base priority value is. For the secondary command, it's removing 1 increment of 4096. So 32768 drops down to 28672. I know my math isn't exactly 100% spot on, but you get the point. But that's basically how that would come into play. And that is pretty much it. If we jump out of global config and do a show spanning tree protocol, if I look here, we're going to see that gig 2 on switch 31 is the root port, and gig 3 is the alternate port. And the way that it detects that is if there are 2 connections between me and another switch, I will always choose the lower port ID to be the winner of whatever it is I'm trying to elect, whether it's the root and the alternate, or whether it's alternate and the root port. So if I was to look at, say, switch 29 for VLAN 11, 12, show spanning tree VLAN, we'll see that designated forwarding. So you'll see here on this guy here that we have 0 and 1, and then 2 and 3. So for VLAN 11, my root is gig 2, and my alternate is gig 3. But for the other two ports, 00 and 01, and then 1/0, those are all designated forwarding because they're downstream facing. So any downstream facing port away from the root bridge is designated forwarding. And that's basically how that would come into play. That's really it. I mean, beyond that, anything you dive into deeper onto how Spanish tree protocol works, you're just going to be getting into some of the optimization aspects. That's literally all you're going to be doing. So that's basically how I wanted to break it down in terms of how it works, because there's really not much more to it than that. There are other mechanisms out there like multiple spanning tree protocol, which I'll go ahead and I'll talk about just briefly because it's on the blueprint. But MSTP is actually pretty simple. Now, remember me talking about how every VLAN that's created on a switch there's going to be a Bpdu sent out every 2 seconds on every trunk link. So if you have 50 VLANs, that's going to be a lot of control plane traffic. Well, you can eliminate that per VLAN Bpdu hello being sent by switching over to multiple spanning tree protocol. So in order to do that, you just type in here spanning tree mode is going to be multiple MSTP. And if you come in here, spanning tree MST configuration, and go underneath here, then you can specify the instance ID and things like that. So you can specify the instance, and you can specify, we'll type in, we'll say instance 0, and the VLAN range that you're going to map to this. Now this is instance 0. Think of this like, I'm not sure exactly, like the default instance. Everything goes into 0 out of the gate. So if I wanted to, I can create, we'll type in 1, 11, 12, we'll say 21, and 22. And then there I go. And then I can type in revision number is going to be, we'll say 10. And that's all I can, and then the name is going to be, we'll just say ENT default. Okay, so that's basically how that would come into play. If I do a show spanning tree, you'll notice that I'm in MSTP, and you'll notice that a lot of this stuff it's got a much different look and feel. But notice how everything is MST, and that the cost has skyrocketed. Before it was much, much lower. It was 4, and so on and so forth. Now it's much higher, 20,000, so on and so forth. So what I'm going to go do is, when we look at this, we look at the show spanning tree MST and look at I think it's the detail. It doesn't really give you a whole lot. You have some informational details here that it can be a little tricky to read through all this stuff and how it's laid out. But the main goal that we're looking at here is, we're looking at this, we see VLANs mapped as 1 through 4094, right? So we're saying all VLANs belong to this instance. So in a situation like that, we have a bunch of information being sent out, but it's only one Bpdu. Now, if I was to go create another instance, spanning tree MST configuration, and say instance 1, VLAN is going to be, and I'll say this will be the odd VLAN, so this will be a 1, 11, 21, 23, 25, 27, right? And the type of name is going to be odd, and then the revision is going to be, say, 11. And I jump out of global config, and I do notice how we do a show spanning tree. Now I'm going to have 0, and I'm also going to have 1. and MST instance 1 detail. This one here shows me that I have 1, 21, 23, 25, 27. So what I'm going to do is for these specific VLANs, I'm going to send out one Bpdu for all of these VLANs. That's basically what that comes into play. Now let's go ahead and do spanning tree MST configuration. I'm going to type in the instance 2. It's going to be VLAN 12, 22, 24, 26, 28. The name is going to be even. And the revision is going to be 12. And that's been created. So we see that that guy's squared away. Now we come down here and we look at the show spanning tree. We can see we have 0, we have 1, and then we have 2. But you can't tell a whole lot is there by looking at this. So we look at 2, we can see we've got 12, 22, 24, 26, 28, so on and so forth. So now I do a show run. We have not sure exactly. So we have we have the name. I'd have to probably create multiple instances here, but this just gives you an idea of how that would come into play. So we have a couple of different instances and everything's coming together. And that's basically multiple spanning tree protocol. I mean, there's really not too much more to it than that. Let me go ahead and just drag this information right here over towards the other switches. Let's go here. And then 31. Alright, so now we go back to 29. So now we should be pretty much, things are going to start clearing up for us. 2 is, now they're starting to clear. So now we should be squared away. And really now, because we have 2 instances, 0, 1, and 2, what will end up happening is for those specific VLANs, if there's a change, we're going to send one Bpdu out, but it's going to be sent for all those VLANs. So if you have a very large VLAN database, you can simply send one Bpdu update out through multiple spanning tree protocol and be squared away. That's MST. I mean, I've never used it in production because no environment has ever been big enough to use it. So my experience with it is only when I've labbed it up, and the basics to it are what I've shown you. I don't see you needing to know much more beyond that. There are some other details to it, but I will let you default to reading some documentation up on it and leaving you to your own devices with multiple spanning tree. With that being said, ladies and gentlemen, thank you so much for stopping by, and we'll catch you guys in the next video.